This $18 device can make your home electricity up to 95% cheaper during heating season, and it does not need a single solar panel to do it. It is called a thermoelectric generator module. It's the size of a drink coaster. It turns any wood stove into a silent power plant. No moving parts, no fuel cost, no maintenance. It runs on waste heat your stove is already throwing away, and it produces enough electricity to power your lights, charge your phone, run a radio, and keep a laptop alive indefinitely. NASA has been powering deep space missions with this exact technology since the 1970s. Yet across 84 million American households that burn wood, gas, or pellets every winter, almost nobody has been told this exists. By the end of this video, you're going to know exactly how much electricity this device pulls from a stove you're already running. You'll know what that saves you over a full winter. You'll know the 4 parts you need, what each one costs, and where to order them. You'll know how to set up the whole system in a single afternoon, with no electrician and no special tools. I'll show you how to tell whether your stove runs hot enough to make this work. And then, I'm going to show you why a $400 billion power industry has made sure you've never seen this device. Not at a hardware store, not at a home improvement center, not on a single federal rebate list in America. But first, you need to see what your stove is actually wasting right now. Because when you realize how much free electricity is floating up your chimney every winter, you're going to be furious. According to the U.S. Department of Energy, the average American home loses 20 to 30% of its heating energy as waste heat. That is hundreds of dollars literally floating out of your flue pipe every winter. A thermoelectric generator harvests that energy at a conversion cost approaching zero, because the fuel is heat you have already paid for. Now here's the part that matters. A single $18 module is not going to replace your electric bill. You need to understand that clearly. One module produces 5 to 15 watts, depending on the temperature difference between your stove surface and the heat sink. That is enough to charge a phone or run a small LED light, but it is not running your refrigerator. The real power comes when you stack 4, 6, or 10 modules together with proper cooling. A 4-module system with a good heatsink and a charge controller produces a steady 40 to 50 watts, 24 hours a day, for the entire heating season. Over 6 months of winter, that is roughly 140 kilowatt hours of electricity generated from heat that was otherwise going straight up the chimney. At the national average electric rate, that is $22 of free power per season. The system costs $60 to $200 in parts, and it lasts 8 to 15 years with zero maintenance. For off-grid cabins and homesteads, the cost per watt-hour is a fraction of what a comparable solar panel setup would run. That gap widens during the winter months, when solar output drops and your stove is running hardest. That is where the real savings calculation gets interesting, and that is why this technology matters. The thermoelectric generator is not a new invention. The physics behind it dates back to 1821, when a German physicist named Thomas Johann Seebeck noticed something strange. He connected 2 different metals in a loop and heated one junction while keeping the other cool. A magnetic compass needle nearby deflected. He had discovered that a temperature difference between 2 different conductors creates a voltage. He called it thermomagnetic effect. The scientific community later renamed it the Seebeck effect, and it became the foundation of every thermoelectric device that followed. Seebeck never built a generator. He died in 1831 without realizing the commercial potential of what he had found. But within decades, other scientists began stacking thermocouples in series to amplify the voltage. By the 1850s, a Danish physicist named Hans Christian Ørsted had demonstrated that arrays of bismuth and antimony junctions could produce measurable current from a candle flame. The concept was real, repeatable, and completely ignored by the emerging electrical industry that was busy building turbines and dynamos. Then something remarkable happened on the other side of the world. In 1954, Soviet scientist Abram Ioffe at the Leningrad Physico-Technical Institute developed the first practical thermoelectric generators using doped semiconductor materials. He replaced the crude bimetallic junctions with bismuth telluride compounds, and the efficiency jumped from less than 1% to over 5%. Ioffe published his results openly. He envisioned thermoelectric power for rural Soviet homes that had no access to the electrical grid. Kerosene lamp generators were deployed across remote Siberian villages, a lamp that provided both light and electricity from the same fuel source. The Soviets were using stovetop thermoelectric generators in the 1950s, 70 years before most Americans ever heard the term. But the story that truly proved this technology on the largest stage was not on Earth at all. It was in space. In 1961, NASA launched the first radioisotope thermoelectric generator on the Transit 4A navigation satellite. The device converted decay heat from plutonium-238 into electricity using the exact same Seebeck principle from 1821. It worked perfectly. NASA never looked back. Every Voyager probe carries 3 RTGs that started at 158 watts each in 1977. Voyager 2 was still producing 225 watts in April of 2024. That is 47 years later, 15 billion miles from the Sun. No maintenance, no fuel tank, no moving parts. The Mars Curiosity rover runs on a multi-mission RTG that started at 120 watts in 2012. The physics is identical. The only difference between the device powering a spacecraft at the edge of interstellar space and the one you can clamp onto your wood stove is the heat source. But here is where it gets personal for you. The mechanism that powers a billion-dollar space probe is available as an $18 ceramic plate on industrial supplier websites right now, and almost nobody is buying it. The modern chapter of stovetop thermoelectric generation began in 2012. A Welsh inventor named Tecwyn Twymfat ran a small workshop called Goat Industries. He decided to find out just how much electricity a wood stove could actually produce. He purchased 10 high-temperature thermoelectric generator modules, rated for 250 degrees Celsius. He built a custom aluminum mounting bracket and bolted the modules directly to a wood-burning stove. He ran copper water lines through a radiator on the cold side to maintain the temperature differential. Then he wired the modules into 2 parallel strings. The result was documented on video and published to Instructables. At 13.8 volts under load, his system produced 120 watts of continuous electricity from a single wood stove. That is enough to power 10 LED floodlights, a circulation pump, and a cooling fan simultaneously. He ran the entire system on nothing but firewood. Twymfat was honest about the cost. The 10 high-temperature modules were expensive, several $100s total, and the water cooling system added complexity. He noted that most people would not want to replicate the full 10-module system, but he also built a single module version that produced roughly 12 watts for a fraction of the cost, and he documented every step. Around the same time, a French research team at the University of Lorraine was testing thermoelectric modules on large, multifunctional mud stoves based on traditional Moroccan designs. They installed 8 modules at the base of a built-in 30-liter water storage tank. The tank served double duty. It was the cold side heat sink for the thermoelectric modules, and it was the household hot water supply. A later prototype in 2015 used 21 modules with pumped water cooling and produced between 25 and 166 watts, depending on the burn rate. At peak output of 9 kilograms of wood per hour, each module was producing 7.9 watts. That is nearly double the output per module of a system using passive air cooling. But the real proof that mattered was not in a lab. It was in the hands of ordinary people, building these systems in their cabins and homesteads during the 20-teens. And the numbers they were reporting would change how you think about winter electricity entirely. Now, if you are thinking this sounds too good to be true, that is the right instinct. A 5% efficient device does not sound impressive on paper, and you are right. The U.S. Department of Energy puts commercial bismuth telluride thermoelectric efficiency at 5 to 8%. A paper published in the journal iScience in 2020 demonstrated a breakthrough module hitting 8% efficiency. The authors described that as 40% higher than the best commercial modules available. So, let us be honest. Thermoelectric generators are not efficient compared to solar panels or gas turbines. But efficiency is not the right metric here, and here is why. The Seebeck effect works because of a property of certain semiconductor materials called the thermoelectric figure of merit. Scientists call it ZT. In bismuth telluride, the ZT value peaks near room temperature to about 250 degrees Celsius, which happens to be exactly the temperature range of a wood stove surface. When you heat one side of a thermoelectric module and keep the other side cool, something happens inside the doped semiconductors. Charge carriers, electrons on one side and holes on the other, migrate from the hot junction to the cold junction. That movement of charge is direct current. No magnets, no turbines, no combustion. Just physics converting a temperature gradient into voltage. The key is the temperature differential. The greater the difference between the hot side and the cold side, the more voltage the module produces. A stove surface running at 200 degrees Celsius with a heat sink at 30 degrees Celsius gives you a delta T of 170 degrees. That is where the 10 to 15 watts per module comes from. Now, here is the part most people get wrong, and it is the single most important thing to understand if you are going to build one of these. The cold side matters more than the hot side. You can have the hottest stove in the world, but if your heatsink cannot pull heat away from the cold face of the module fast enough, the delta T collapses. Your output drops to nearly zero. This is Fourier's law of heat conduction. Heat flows from hot to cold at a rate proportional to the temperature gradient and the thermal conductivity of the material. A cheap aluminum fin heatsink in still air might give you 5 watts per module. The same module with a fan blowing across the fins might give you 12 watts. Water cooling changes the game entirely. Cold water circulates through a block on the cold side and carries the heat away to a radiator. That same module can push past 15 watts, and the efficiency question actually flips when you look at it from a different angle. Solar panels convert about 20% of sunlight into electricity, but sunlight costs zero. Thermoelectric generators convert 5 to 8% of heat into electricity, but that heat also costs zero, because it is waste heat from a stove you are already running. When the input is free, the efficiency percentage becomes irrelevant. What matters is the output versus the cost of the hardware, and that is where thermoelectric generators destroy solar on a dollar per watt basis for winter supplemental power. The real-world numbers tell the story better than any lab report. Verified DIY builds on off-grid forums document 4 module systems producing a steady 47 watts around the clock during the heating season. That is enough to charge batteries, run LED lighting, and power a phone and a radio. It will keep a laptop running indefinitely, all from a stove the homeowner was going to burn anyway. A low-tech magazine analysis of thermoelectric stove generators compiled data from multiple prototypes. A French system with 21 water-cooled modules on a large wood stove produced 166 watts at peak burn rate. Even at a modest burn of 1 kilogram of wood per hour, it still produced 25 watts. The pump consumed 5 watts, leaving 20 watts of net free electricity from a stove that was already heating the house and the water. Perhaps the most remarkable real-world validation comes not from a cabin, but from outer space. NASA's Voyager 1 RTG has been converting heat to electricity in the vacuum of interstellar space since 1977. It started at 158 watts. In 2024, 47 years later, it was still producing enough power to run 5 scientific instruments at 15 billion miles from Earth. No moving parts failed. No wiring degraded beyond function. The thermoelectric junctions inside those generators are fundamentally the same bismuth telluride-based compounds you can order online for $18. On the ground, a 2015 case study from a remote cabin in British Columbia documented a homeowner running a 2-module Tegmart system on a Pacific Energy wood stove. The total system cost was $189, including the charge controller and a small sealed lead-acid battery. The system produced enough electricity to run 6 LED lights, a marine radio, and a USB charging station from October through April. The homeowner estimated she saved between $150 and $200 per season in avoided generator fuel costs. In developing countries, the stakes are higher. A 2016 study published by the University of Glasgow tested thermoelectric generators on cook stoves in Malawi. A single module producing 3 to 5 watts replaced kerosene lamps for lighting and eliminated the need for disposable batteries for radios. The annual savings for a rural family was over $40, in a country where the median income is $600 a year. So if this technology works in interstellar space, works in a Welsh workshop, and works in a French research lab, why is it missing? If it works in a Canadian cabin and a Malawian kitchen, why does it not appear in a single American home improvement store? The answer is not a conspiracy. It is a system designed to be blind to anything it cannot meter, finance, or regulate. The $400 billion grid electricity industry in the United States is built on centralized generation and metered delivery. Every incentive in the system, from utility rate structures to federal tax credits, is designed to reward technologies that feed into or reduce demand from the existing grid. Solar panels qualify for the federal investment tax credit. Wind turbines qualify. Heat pumps qualify. A thermoelectric generator module does not qualify for a single federal energy incentive in America. Not one. Not because it was reviewed and rejected, because nobody in the regulatory apparatus has ever written a category for it. The Department of Energy does not list thermoelectric generators in its Consumer Energy Guide. Energy Star has no rating for them. ASHRAE, the standard-setting body for heating and cooling systems, has no performance specification for residential thermoelectric generation. The technology falls into a regulatory void. It is not banned. It is not restricted. It simply does not exist in the language of the system that decides what qualifies for support. And here is the reframe you need to hear. We are told that the grid is the sophisticated modern solution, and that off-grid devices like thermoelectric generators are primitive backwoods curiosities. But the grid requires billions of dollars in infrastructure. It burns fossil fuels at 35% average thermal efficiency. It loses 6% of generated power in transmission lines, and it charges you a monthly fee to access electricity that a ceramic plate the size of a coaster could produce from heat on top of your stove for free. The thermoelectric generator has no fuel cost, no transmission loss, no billing cycle, and no moving parts. It produces electricity at the point of use from energy that would otherwise be wasted. Tell me again which one is the primitive solution. The solar industry receives billions in federal subsidies. Thermoelectric generators receive zero. Not because TEGs do not work, because the system was never designed to see them. But here's what you can do about that right now. A basic stovetop thermoelectric system requires 4 components. First, the generator modules themselves. Do not buy Peltier cooling modules from generic electronics suppliers. They look identical, but they are designed for cooling, not power generation, and they will burn out in weeks. You need modules specifically rated for power generation, rated for hot side temperatures of at least 200 degrees Celsius. Second, a heatsink. A finned aluminum heatsink with a small 12-volt fan is the minimum. Water cooling is better, but adds complexity and cost. Third, a charge controller. A solar charge controller rated for 12 volts works perfectly. And fourth, a battery. A sealed lead-acid or lithium iron phosphate battery stores the power for use when the stove is not running. Tegmart, based in the United States, sells complete kits and individual modules designed specifically for wood stove applications. Their modules range from 3 watts to over 20 watts each, with prices starting at around $25 per module. A full 4-module kit with heatsink, charge controller, and wiring runs between $150 and $200. You do not need an electrician or any specialized skills beyond the ability to bolt a bracket to a stovepipe and connect a few wires. Plan on an afternoon for the installation. One more warning. Poor thermal contact is the second most common failure after overheating. If you just set the module on the stove surface without thermal paste and clamping pressure, you will get a fraction of a watt instead of 10. Apply a thin layer of high-temperature thermal compound to both faces of the module. Then use a bolted clamp bracket to press the module firmly between the stove surface and the heatsink. Without that contact pressure, heat cannot flow through the module and no electricity is produced. Be aware of two critical limitations. First, overheating. Bismuth telluride modules have a maximum hot side temperature of around 250 degrees Celsius. A roaring wood stove surface can easily exceed 300 degrees. If you overheat the module, the internal solder junctions melt and the device is permanently destroyed. A surface thermometer on your stove is not optional. It is a requirement. Second, this is seasonal supplemental power. If your stove runs 6 months a year, your TEG produces electricity 6 months a year. This does not replace a grid connection or a solar panel system for year-round needs. It fills a specific role. Free continuous electricity during the heating season, when solar output is at its lowest and your heating fuel is already being burned. The thermoelectric generator is a 200-year-old answer to a 21st century problem. It converts waste heat into usable electricity using the same physics that has powered NASA missions for half a century. $18 per module. No moving parts, no maintenance. A lot of what this channel covers works exactly as claimed and costs less than what replaced it. It was set aside not because it failed, but because the system was never designed to see it. If discovering the lost science of energy independence matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. Now here is a question I want you to answer in the comments. If you had a reliable 50-watt thermoelectric system on your wood stove, would you use it as your primary winter power source for lighting and devices? Or would you keep it purely as an emergency backup for outages? Let me know which path you would choose.